Welcome everybody to this week's installment of our reading group. Today, really excited to welcome Yunzhi Yao, who will be presenting his work on knowledge circuits in pre-trained transformers. Yunzhi is from Zhejiang University. Again, I think I've pronounced that terribly, but the work was done in collaboration with Zhejiang University and the National University of Singapore with several co-authors. But I won't give the intro. I'll let you introduce what you're doing. So the floor is yours. Yeah, take it away.
Hello, everyone. I'm very honored to be here to share our work, the knowledge circuits in pre-trained transformers. It's collaborated with Shumin Deng from the National University of Singapore, and I am Yunzhi Yao from Zhejiang University, and I'm currently a PhD candidate in natural language processing. So today's content is in three parts. The first one, I will introduce the background and motivation of our work, and the second one is how we discover the knowledge circuit and some of our findings. And in the third part, I will do some analysis and discuss the future of this work. So the first part is the background and the motivation. When we do this work, we first rethink the currently knowledge storage in transformers. In previous work, we most think that the feed-forward networks in transformers store enormous knowledge in them, and the most popular work is knowledge neuron, which show that some column in the feed-forward network, it can be seen as a key value memory, and there are some of them store the corresponding knowledge, and we can find them through the integrated gradient method. However, recently there are some works that find that if we edit the knowledge neurons that we have identified, it is not enough to overturn the predictions of the language model it gave us. And in this year's earlier paper, what does the knowledge neuron thesis have to do with knowledge? They find that if we change the knowledge neurons, they conduct experiments both on the syntactic and factual datasets, and they found that the prediction of the language model rarely changed. So it means that the feed-forward network or the knowledge neuron we found is not enough to it's not enough for the language model to give us the correct answers. So since the knowledge neuron is try to they view the knowledge as a model origin in the language model that account for the knowledge storage, and this assumption neglects the role of attention head in the language models. And in previous experiments, we found it is not enough to understand the knowledge in the transformers. So here we try to think, what about, is there some connections that in the language models that they collaborate together to store and express the knowledge? And in Google in last year, they have found some connections in the language models, and they show that the knowledge in the factual associations in the pre-trained language models, they have three parts. The first phase, at the subject last token positions, the model would undergo a subject enrichment. At the subject token's place, the hidden steps would aggregate some features of the subject. And also there are some attention head, also there are some, the second phase is the relation propagation. The model would gain the relation in the context, and finally in the later layers, some attention, they would extract the attribute from the subject position to the last token to give us the final answer. And they do these experiments in some models, and and it just gives us an assumption. But we think that if this is true, we can find some computation graphs in the language models. So this is circuit. So I want to first introduce the circuit, the definition. Circuits are subgraphs of the network, and they consisting of features and weights that connect them. So let's recall what the structure of the transformer. First, the transformer is a residue stream, and each layer it contains both the self-attention head and the multi-layer perception, the MLP. So each layer's output, here we did, here we denote it as RL. It can be represented as the previous layer's output, the RL plus 1, and add the sum of each attention head's output and the MLP layer at these layers. And if we recursively write these equations, we can find that the input of each attention head, it is the sum of the embedding. Here we denote it as R here, and all the previous layers, MLP's output and the attention head's output. And for the MLP layer's input, it also can be described as the sum of the embedding and the MLP's output and each layer's attention head's output. So based on this, we can view the
very good question. Sorry, what does R mean? Does that mean response? Sorry, I didn't fully follow on the top equation.
Okay, here R is the embedding output. Yeah, it's the
okay. So it's the out. Okay, so it's like some intermediate layer, basically.
Yeah.
And is A the activations, or what's A?
A is the attention head. Here, for example, the ALG, it means the G's head at the layer L.
Okay, got it. And then M is the like weights, or what's M?
M is the MLP here. Yeah.
Okay, got it. Okay, fine.
Yeah.
Okay. Sure. Okay, and then same with the ones below. The sum again is the attentions, and the sum again is M on the MLP. And then I is, and sorry, is I the input, or
R is the embedding output. Here is
okay.
R0. Yeah. It is the output of the zero layer. Actually, it is just the embedding layer.
Okay. Okay, got it.
Yeah.
Okay, makes sense. Cool. Thanks.
Yeah. So we can see that each component in the transformers input, we can connect them with the previous layer's component, including the MLP and attention head. So we can view it as a computation graph. And a circuit is the subgraph of this network. And here is an example they found in previous in GPT-2 small for the indirect identification object. I will show it in the next page. Yeah, here. A previous work, they found some circuits for some tasks like the indirect object identification. This task, here is an example with Mary and John went to the store. John gave a drink to, here we want the model to give us the answer, Mary, who is the indirect object in this sentence. And they found some interesting attention head in the transformer. This is a GPT-2 small model. Such as the previous token head, which would attend the token with its previous token. And the most important attention head they found is the name overhead, which would attend to the indirect object. Here is a Mary, and they would give it make the Mary as the output of this attention head, and which is make the model give us the final answer maybe. So this is the circuit they discovered in before, and based on all this previous work, we believe that there is a circuit in the model that may store and express the knowledge, such as the fact or some common sense or linguistic knowledge. So here we try to see whether we can find these circuits in the language models. So here in the next part, I want to show how we discover these knowledge circuits and some analysis about them. So here we employ the causal inference method to construct the knowledge circuit, and we use the automatic circuit discovery tool, which is published in last year's news, which provided us a pipeline to build the circuits in the language models. And here are some steps. The first step is to view the language model as a directed axially graph. We denote it as G here, and we view them as the computation graph here, and we would first sort it in the reverse topological way, and we would iterate each edge. And for each edge, we would overwrite the value of an edge with a corrupted activation. And here we use the zero ablation in our experiments. For example, here is a simple graph here. If we want to ablate the edge from B to O in this graph, and in our experiment, we just set the input from B to O as 0, which is the zero ablation, and to mitigate this edge from the model's computation. And after that, we would run a forward path through the model and compare the output values of the new model with the original one. Here, to compare their performance, here we utilize a metric. And in our experiment, we want to find some circuits for the knowledge. So in our experiment, we use the knowledge as a triple, including a subject, a relation, and object. And our goal is to give the make the model give us the target object based on the given subject and the relation context. And to measure the performance change, here we utilize the negative log of the probability of the target token here. Yeah, we just use the negative log of the original one minus the one that with the ablated edge. And here we set a threshold here. Here is a total here. If the performance change is lower than the threshold, it may mean that these edges, if we remove this edge from the computation graph, it will not affect the performance of the language model, and we consider this edge to be unimportant. So we remove this edge from the computation graph. And based on this, we would recurse the whole computation graph here and until the full circuit is recovered. And finally, we would get the subgraph that contributes to the knowledge expression. So the node is the attention and the MLP in the language models, and the edge is the computation in the language models here. So this is the construction. Oh, yeah.
How is the threshold T determined? Is the threshold just chosen arbitrarily, or?
It's a threshold to choose. It's a hyperparameter. We set it to different values to.
Okay, makes sense.
Yeah,
I was going to say
it may. In our experiment, we usually set that 0.01. If you set it too large, it may
Yeah.
It may prove too much connections. Sometimes you may not got a full computation graph.
I would have thought that, I guess it becomes very computationally expensive, but I'd have thought that you could analytically determine whether or not for a given sentence, a given input prompt, I'd have thought that you could remove the connections that you know will not change the output at all, and you continue to remove those least important connections until you would start to change the output. And I wouldn't have thought you would need an explicit threshold hyperparameter, but maybe I'm not thinking about it clearly enough. Because obviously, if you like have these contributing connections, there'll be some connections that make no difference at all to the output that's streamed, and I'd have thought you can just keep removing the least important until you observe a change in the output. But anyway, yeah, I mean, we don't need to unpack all of that, but suffice it to say that this is just a hyperparameter that's chosen and you can vary it basically.
Yeah, and
Okay.
and it's right that it may be consuming to do this computing.
Yeah, but it would
Yeah,
technically be possible to like analytically determine exactly how many to prune until you know that the output is unchanged from the pruning. And if you did that, you wouldn't need a hyperparameter and a threshold. Or am I misunderstanding something here?
mm, in our experiment, we just iterate all the edges in the model.
Okay. Yeah,
And
well, I think I understand. Keep going. Maybe just keep going for now. I'll obviously see on the next slide. But yeah, but that answers my question. It's just selected and you can vary this. It makes sense.
yeah, oh, okay, I will just keep going. And
Yeah, sounds good.
okay. So so after we get the identified circuit, we want to know is it truly responsible for the specific knowledge type. So here we construct a data set and we split into the validation and the test uh, set. Here, for example, in the here I give an example of the knowledge, like which city is located in the city is located in which country. For example, in the validation set, we said the Rio de Janeiro is located in the country of Brazil, and based on the validation set, we will construct a circuit here, and after we got this, we would test its performance on the test set, which the knowledge is not seen on the validation set. Ideally, we want the circuit to keep the performance of the original model on the validation set and both on both the validation set and the test set. And to measure this change, the performance here we use the heat Chen here. It means that giving the output of the logics of the language models, we map it into the embedding space and we see whether the target token is in the top 10 vocabulary space here. If it appears as the top 10 tokens in the vocabulary space, we will say that the language model give us the target token as the answer.
Very quick thing. Sorry, I understand why you need a threshold now. Sorry, I thought the knowledge circuits were just for one input prompt. So if it was just the circuit for this specific input prompt, then you could reduce the entire thing down without needing a threshold, just to the exact nodes that are needed for that exact input prompt. But given that you have this test set and validation set, and you want to determine the circuit for a broad like prompt type and a kind of a prompt template, then yeah, it makes sense why you need a threshold because you can't do it analytically. Yeah, sorry, just it makes sense why you need that threshold.
Yeah. And we do experiments on both the batch input like these different, like the prompt of different subjects and objects, and we also conduct some experiments on the single fact or single.
Okay, got it. Yeah, because on the single prompt ones, you could actually just determine the minimum number of connections to reproduce the exact same output as before, and you wouldn't need a threshold. But in the case where you're doing it here, you do need the threshold. But yeah, anyway, it makes sense to me. Yeah.
Okay.
Thanks.
I keep going. So here is the performance in GPT-2 media. Yeah, and here is, for the validation set, the original result is always 1 or nearly 80%. It means that since we select the knowledge that the language model already know here, and we can find that on the validation set, or only based on the circuit, we can keep more than 17% of the performance of the whole language model here. And surprisingly, we can find that on the test set, under some knowledge type, we can even see a performance increase here. And we conduct experiments on both the several type of knowledge, including the linguistic, common sense, factual, and bias here. And the improvements on the test set, it demonstrates that our circuit is responsible for this kind of knowledge type and all this kind of relation prompts. And if we remove our other unrelated computation in the language models, it may make the language model give us the more accurate results. So in the previous part, it's the identify circuit on some knowledge types, and we want to further analyze the information flow, or what's the component in the circuit, how they work, and what they do, and how they collaborate together. So here we just run some cases in the language models, and here is an example for this knowledge. The official language of France is French, and this is the circuit we got GPT-2 media. Compared to the origin model, it's quite sparse, but it's also a bit complicated here. And in our experiment, we try to analyze each component, but we found some of them currently I cannot understand their behaviors. But also there are some nodes exhibit some common behaviors, and based on these nodes, I simplify this circuit as the left part in this page. And to analyze the components behavior here, I just utilize the logic lens, which just map the output of each node. Here is the NLP, or the attention head, to the embedding space, and to see the outputs of each component in the circuit and in the vocabulary space. Here we first view it at a layer level. For example, each layer's change of the target token. Here in this case, the official language of France is we want the language model give us the answer French. Here we draw the rank of the French in each layer's output on the vocabulary space, and we can find that here is this line. We can find that at layer 17, the French has become the token of top 1 in the vocabulary space. It means that if we just use the layer 17's output to give us the correct answer, it will directly give us the French here. And we can say that just after the 17th layers, the probability of the French token is become to increase. And this is enhanced by the following layers here. And we back to the So here we find that the MLP 17 here, it is a node that bears a lot of other components inputs. So here we try to analyze these different attention head here to see what they contribute to the MLP 17's computation. So here we found some heads that bear some common behaviors, and we show them in this page. We found two kinds of heads. The first one is the mover head, and the second one is the relation head. The first is mover head. The mover head is the kind of attention head that would move the information as a subject position to the last token. This is also found in previous works, and we found them in the knowledge type. Here is for example, the attention head in layer 14 and the seventh head in layers 14. It is attends the last token to the subject France here, and we find that its output is related to some French words and some French literatures here, like Franc, Francis here. And also there are other kinds of attention head that is the relation head here. They would attend the relation token in the context. For example, the 17, the 13th head in the layer 17, in the layer 14. They attend the last token to the language, and they would output some information about these tokens, like language or dialect. And we want to see, and here is also the first attention head in the 15th layer here. It is kind of the mixture head, they both, but it mainly attend the last token to the France, and it also give us some information about French. And the French is actually the information it gives to the MLP 17. And based on these tokens outputs, the finally MLP 17 give us the final answer French in the language models. And we also find these different kinds of attention head in Tiny Llama, which is 1.1 billion language models, and they show similar behaviors. For example, in this case, the marathon of Tarimago is also French, and we also see that before at nearly about layer 17, it appears as the top 1 token in the vocabulary space, and after that, the probability of French began to increase. And we also found some mover head and relation head. For example, the 11th head in layer 15, it would attend to the tokens in the some subject tokens and give us the French and or France some related tokens, and some other language or relation head that would attend to the mother tongue token here, and it will give us some other language information like English here.
There's a quick question in the audience, actually. So Yara asked, your model is trying to figure out the right connection between layers that contribute to the final output, or trying to build another model with less computations. Didn't get this point. Yeah, so do you have an answer to that, Yunzhi?
Sorry, I didn't get.
I guess they're kind of similar. I guess, well, I from my understanding at least, one of the main motivations here is actually understanding like how the LLMs work. Is that a fair thing to say? So the question was whether the end motivation is trying to figure out the right, basically trying to figure out the right connections between the layers that contribute to the final output, or whether the end goal is actually to build a model that is more efficient to run. I guess maybe they both go hand in hand, but my understanding is the main motivation is explainability. Is that correct?
Yes. Our main contribution or motivation is to be better understand the computation.
But that is a great question though that Yara brings up, which is whether finding these subgraphs could actually also improve computational efficiency. Is that something that could be the case, particularly if you're running it on a CPU or something maybe? Do you have any thoughts on this?
Well, I didn't do experiments here, but I think it may be
Yeah, because
good
I
to
guess
the
you would end up
computation here.
reducing the computation, right? So you would end
Yeah,
up having. So I guess like yeah, it's a very good point. I mean, I guess it makes you think if like an alternative to fine tuning an LLM for a particular task could be to find the circuit that aligns to that task, use that as a starting point, and then you already have removed a lot of the computation that is not needed for other. I guess the question is, how complex are the circuits for like yeah, anyway, so it's a very interesting point. Yeah, we can discuss this at the end, I guess. Yeah, anyway, let's let you carry on, and maybe we can open that debate at the end of the talk. Yeah.
Okay. Okay. I will first keep going, and we will
Yes.
start in later. Okay.
Sounds great.
So yeah. And here we just see the distribution in the language models. Here we conduct experiments on some like GPT-2 medium, GPT-2 large, or tiny llama on different kinds of knowledge, and we found that they both show that just before the last layer of the language model, just in the middle to later layers, the language model would give us this answer, and we can see that based on these findings, most of the circuits components they are distributed in the middle and front part of the model, and in the later layers they would enhance or improve the probabilities of the token in the top one here, and we will see some more cases in the later presentations and to see this phenomena more clearly. So, and here I just list some spatial components for different kinds of knowledge here, like in Tiny Llama, for example, the first head in layer 17, they may mainly to deal with some word past tense knowledge here. A very interesting finding is that I found that the circuit I discovered in Tiny Llama is more sparse than GPT style language models. But I didn't do more investigation here, but I guess that Tiny Llama may be more able to store the knowledge than GPT-2 Large, but I think it's an open question to discover in the future. And so the next part is the analysis and the discussion. So, when we found the knowledge circuits, we want to try to see how we edit the language model may influence the knowledge circuits we discovered. So the first thing is what happened when we edit the model. So in this page, I will briefly introduce the knowledge edit and a very popular and strong method for editing the knowledge in the language model. So knowledge editing is aimed to alter the knowledge in the language model and avoid influencing other unrelated informations. For example, if the language model, we ask the language model who is the president of the US, it gives us Joe Biden, and we want to change it from Joe Biden, change it from Donald Trump to Joe Biden. It's just a case here, and we just want to modify a piece or some areas in the language model to quickly change the knowledge in the model without tuning here. And here, and the right part is the method ROM, the rank 1 model editing. It is a quite strong baseline here. And what they do is to edit the second linear matrix in the feed-forward layer here. And this is their computation, but I just briefly introduce it. Here the key is the context representation of the subject and relation here, and the value here is a value of the output of the key here to make the language model give us the correct answer or the correct knowledge as the output here, and they optimize the V star here, and after they get the V star here, they would compute the minimize problem here based on some matrix calculation here, and they finally get the edited weight of this linear matrix in the feed-forward network. And in Rome, they just added one layer feed-forward networks matrix, linear matrix here. So the computation is quite low, and the performance of this method is quite good in several knowledge editing benchmarks. So here we want to see is this a success to change the language models knowledge. So here we conduct experiments on both ROM and fine-tune, and we edited the same area, which is the first layer's feed-forward network's second linear matrix here. And the example here we show is the platform controller hub is created by, in the original model, they give us Microsoft as the output, and we need to change it from Microsoft to Intel. And in our experiment, we found that ROM and fine-tune we show different kinds of influence to the language model or to the knowledge circuits we found. Here, and I want to show the difference of them. So the ROM, we first see the change of the inter token across the layers. So here we can see that if we added the first layers by the ROM method, it at around the 15th layers, it appears as the top one token here, and after that, the probability began to increase. And we see that the attention head at the third attention head at layer 15, it extracts the correct answer intel here, and after that, the language model gives us the intel as the answer. And in the last picture, we can see that before we added the language model, this attention head, they fail to extract the intel information here, and we can see that the behavior of this mover head has changed by the ROM editing. But for the fine-tune method here, we just fine-tune the second linear matrix in first layers, and we find that the language model would directly give us the answer, the intel answer at the layer we edited the model. And after that, the last layer, the later layers behavior will fail to influence this information. And actually, the computation graph or the circuit we get after we use the fine-tune method, it's just the MLP we added in the language model here. So you will find that ROM tend to follow the knowledge circuits. We find that they add the information at the subject position. So the mover head would extract the true answer, but fine-tune is prone to add the knowledge at the specific edit position. But despite the success of ROM, we also find that it may not edit the the specific knowledge here. We find that if we edit the platform controller hub, the creator of this controller hub, it will influence other unrelated knowledge. For example, the Windows Server 2003. Before editing, it give us the model give us the correct answer Microsoft. But after we added the platform controller hub, it will also give us the Intel. So it's changed. And we also show the difference between ROM and fine-tune, despite they both failed at this case. And we can find that fine-tune, fine-tune here it also give us even if we added the inter platform controller hub here, we change it to Windows Server 2003 at the edit layer. It also give us the fine-tune. It give us the inter as the answer. And for the ROM method, it's also interesting. You can see that at layer 10 here, Microsoft here is the correct entity, it's the blue line. So it gives us it has already appear as the top token at the vocabulary space. But at near the 16th to the 17th layers, it finally be surpassed by the wrong answer inter here. And so here we analyze the circuit before we edit and after we edit for the Windows Server 2003 creator. And we find that the mover had selected wrong knowledge here. For example, here is the mover head we found in the circuit from Windows Server. The 14th head in layer 18 here. Before edit, we can find that it attends to Windows Server token and it gives us the correct information like Microsoft or server or domain, other information that related to it. But after that, it changed from Microsoft to Intel. So it means that the ROM, despite that the ROM aims to edit the knowledge related to platform controller hub to Intel, but sometimes it may not only affect the knowledge that is associated to the specific subject here. They add the information into the residue stream, but it may also influence other information here, which may lead to the fail of current knowledge editing method and lead to the side effects that other unrelated things may be changed. So here is the here is some case studies here, and we further conduct experiments on different layers across different kind of knowledge types, and we both find that this is the target token rank across layers in ROM editing. Most of them are most of times the edited entity would appear at several layers after the edited layer. For example, here we added the sixth layer here, and at around 15 or even later, it gives us the correct answer. But after that, also there may some cases that ROM may failed, like the superhero as here. But overall, it shows it shows that the edit of ROM would influence the following layers to give us the correct answer. And compared to the fine-tune, we can see a directly drop at the edit layer here. For example, if we edit the layer 6, we would see a slump at these layers, which would directly give us the edited token as the answer of this language model. So in the previous task is about the editing task. Here we and here we also do some little experiments on the hallucination exploration to see in which part of the language model that lead to the hallucination of the language model. In our we just do a single case study here. It is about a factory hallucination. In this case, we ask the language model what is the official currency of Malaysia. Actually, the correct answer is ringgit, but the language model gives us the wrong answer, the Malaysian here. And we see the information flow across layers here, and we can find that before layer 15, the wrong and the correct entity, they are completed with each others. But just at the layer 15 here, the language model will directly push the raw answer Malaysia to the top token as the vocabulary space. And after that, we see the probability increase of this raw entity here. And if we compute the circuit on the official currency of Malaysia, and we can find that the attention head here, this is the first attention head in the 15 layers. It greatly contributes to the computation here, and we can find that this mover head is selected the wrong knowledge here. The Malaysia here and the mixed language model give us the wrong information. And we can see that it's nearly the last layers, the model finally give us the true tokens, but it's too late for the language model to change these predictions here. Yeah, it is just a simple test about the hallucination, and we can find some. I show one case here, but in some other cases, we also see the same phenomena here. And we also do a little case about the in-context learning case. For example, if we ask the language model comparative form of big, it's under the zero-shot settings, the language model usually give us some meaningless letters or wrong answers. But if we give them just one short demonstration, the comparative form of small is smaller here, it finally give us the bigger here. So we compare the circuit of zero shot and one shot here, and we can find that the one shot circuit it just shows some actual attention heads compared to the zero shot circuits, and these attention heads they both show the same behavior here. I show them in the left part. We can see that they both this attention head here would attend the target to sequence with the previous one, and this attention head I can describe it as induction heads, since all of them they would search the present token in the previous place and they attend to the next token here. For example, the is the last subject, is the last token here, and they will attend to the smaller. Yeah, smaller is the next token that appeared in the previous is word here. And also I want to say it's maybe a function head here. For example, the output of this language model of this attention head are all the comparative of different words, which lead to the language model to give us the correct answer here. So this is just the so the in context here and hallucination are just two preliminary experiments to use knowledge circuit to understand some behavior of language models. And I will make a simple conclusion discussion. Yes, so in this work we just found some circuits that are responsible for the storage and expressions of specific knowledge, and we make the preliminary explorations on the internal mechanism of editing and some other behaviors. But there are also still many components in the discovery circuits that still need us to interpret. And another very interesting question is, based on the circuits, how language model utilize them to do reasoning. I just made a very little experiment here. I tried to do some experiment here, but it's a bit difficult to do. But I found a very interesting phenomenon here. That in the language model to do some multi-hop reasoning here. For example, the home country of Terry Magloire is France, and we ask the official currency of the home country of Terry Magloire is actually it gives us the answer franc. And actually, ideally, we hope the language model to do the first hop to recognize the home country of this person as France, and based on the France, it give us the official currency. But when I do experiment, I find that when I test the multi-hop or these two hop circuits compared to the one hop circuit, it seemingly show no difference there. And so I do an experiment to remove the first hop's contact here to just let the language model to do the reasoning based on the second hop's context and the subject here. So with our first hop, I found that found the pre-trained model in our experiment is include GPT-2, Chinese Llama, and Llama, the first version of Llama 3 billion model. They both give us the front here, which means that the language model may skip the first hop here and directly give us the second hop result. But I found that after alignment, like the chat version model, it didn't show this phenomenon here. So I think it's quite an interesting phenomenon here. And I think that it requires further exploration here. So this is all my presentation here, and thanks for listening. And you can get the code of this project at this GitHub repository and the preprint of our paper here. And thank you.
Amazing. Well, thank you so much for such a great presentation. Let's all give a big round of applause for Yunzhi. That was really good. I certainly have a ton of questions, but I can quickly say first of all, if anybody, if anyone in the audience has any questions at all, then yeah, that'd be great to see some. Yeah. So I don't. Well, K.Pi has a question. Do you want to go? Oh no, that was an attempted applause. I understand. Okay. Okay. Well, I'll kick off then with a question. So there we go. Got it that time. Yeah. So I guess one question here is, I don't know if you've seen Anthropic's papers on monosemanticity and extracting semantic features from the activations. And what they've determined is that the number of semantic features is actually far larger than the number of activations. And you basically have, what's the word? You have like superposition between, so basically what you have is a very large number of semantic features, which then are superimposed on a smaller number of activations. And I guess my point being, as the models get larger and larger, do you feel as though there is going to remain meaningful semantic interpretability from these sub-circuits? Or do you think that the circuits will start to get larger and the semantic interpretation of the sub-circuits could become more difficult, especially given that, like what Anthropic's paper talked about is the fact that you actually maybe have these features are actually the things that are building these circuits up, and it's kind of these features that turn on and off, and they interact to form circuits at the level of the semantic features rather than the level of each layer, because you're basically looking at circuits at the level of each layer, whereas actually the real workings is going on a much lower level of, you know, activated features and so on. So I guess yeah, that's the question. How do you think this relates to the semantic feature research of Anthropic, for example?
Yeah, it is. Yeah, I have read the Anthropic's post here. It's also awesome. Actually, in our I didn't show in the representation, and actually in our experiments, we found that for different kinds of knowledge, we see overlap of their knowledge circuits. Yeah, it means that it means that some of the components in the language model or in the circuits, they may be responsible to other or to some different kinds of knowledge or behaviors. Yeah, I think that it is. I agree that the future may play a more important role in the interpretability work.
And the interesting thing, I guess, is that your circuits are higher level, right? So you have circuits where the node is a layer or an attention head, whereas the work with Anthropic, the node is an activated or unactivated feature. So I guess in a way, like what we have in your work is this graph, which is a very coarse, high-level graph. And if you kind of zoomed in, you can have much more nodes at the level of activated features turned on and off, and the knowledge circuitry would become much more complicated and much finer grained, but maybe also more expressive semantically as well, I suppose. That's kind of how I think about it.
Yes, currently I also make this question that some of the node I found is not
Yeah,
easy to understand. So I think that
yeah,
if I just just decompose it as
yeah,
different features, I think that maybe it may give us more insights here. And actually, I'm
yeah,
also trying to combine some sparse autoencoders with the circles. And actually,
yeah.
I have seen some works that are trying to do this
Okay,
recently.
nice. Okay, cool. Yeah, I know it's very expensive. I know that with the Anthropic stuff, they created a data set of billions of activations. Because obviously, what you need to do is you need to run, like, you need to get a large token data set. You need to run the model many, many times. You need to create a data set of the activations, and then you need to train a sparse autoencoder on the data set of activations. So it's incredibly computationally expensive. It's no wonder that their first paper did it on a tiny, like, single layer model, and they did it most recently on Haiku, I think. But yeah, no, I mean that's very interesting. And I guess the final question, very much related to what Yara brought up, which I hadn't thought about, is yeah, do you know if there's much work here on runtime efficiency? Because to be honest, when you fine tune models for particular tasks and so on, and when you do, I mean, this reminds me very much of pruning, right? You have magnitude-based pruning of the weights of a neural network, and actually, there's works applying pruning to the weight matrices of LLMs as well. Now, another form of pruning is, I mean, effectively, this is a form of what's the word? Like, is it dense pruning is what it's called? I'm not sure exactly, but where you basically prune an entire layer. So and pruning, the motivation is very rarely about explainability. The motivation of pruning is predominantly runtime efficiency, memory efficiency, and so on. So I don't know, do you have any comments on the parallels with this explainability work and kind of compression and runtime efficiency work as well?
Yeah, I really think that efficiency and run is an important problem. You know what I do is experiments are always not kind of made because I need to wait a long time to get the surface.
Sure.
I think that we need to find a way that is not that time consuming to get not only to prove the model
Yeah.
but also or just to explain the model. I think that an efficient way is always
Yeah.
better. Yeah.
No, that makes sense. And there could also be some interesting work where you could imagine, like, when the prompts come in, that you know what kind of task it is, and then you know ahead of time what knowledge circuit is relevant for that task, and you can actually avoid querying the entire dense model, and you can just kind of know, well, this prompt is related to this subcircuit of the LLM, and you could almost imagine routing each prompt to like the subcircuit of the large language model that actually is the only needed part, and you don't do all of this wasted computation running all of these layers and activations that you know are not contributing to the final output. So there's a lot of interesting work there, I guess, as well. It kind of reminds me of mixture of depths and things from DeepMind a little bit. Yeah, anyway,
Yeah,
lots of really
I previously was thinking about just use one language model and based on circuit to get some experts of different kinds of
yeah.
to do like a self mixture of experts
No,
construction.
exactly.
But
But
it's
it's,
but
it's
it's
kind
a
of like a
bit difficult.
post-processing mixture of
Yeah,
experts,
yeah.
right? Because you kind of like mixture of experts is trained at the autoregressive phase, whereas in this case you would like detect all of these subnetworks retrospectively once you've like learned how each subnetwork solves different tasks, and then you would kind of like have a dictionary of all of those subnetworks and somehow predict the relevant subnetwork when the prompt comes in. But I don't know. And I guess you would get some runtime efficiency, but that prediction task in itself is quite complicated. So yeah, I don't know if that's quite the solution, but there's certainly some interesting areas to explore that this work uncovers, I think so. Anyway, I could talk all day. I got a dash, and I assume probably you do as well, Yunji. But let's all just give another big round of applause again. If people know where the button is, we might get a few more hands raised. But yeah, really interesting talk. Really great to have you. Obviously, I know you're knocking out papers all the time, so of course we'd love to have you again when you get your next paper out. Yeah, but obviously I know it's also very late over in China right now. I think it's midnight probably now, so I'll let you get to sleep. But it was really great having you. And
Yeah, it's okay. But I seldom sleep this time. I
You're a
usually
night owl.
sleep. Yeah, yeah,
I'm a night owl as well. I get
I
the feeling.
usually
Well,
stay up
I'm glad we
to
didn't keep you up. That's good to know. Anyway, yeah, we'll see you again. Obviously, we'll love to invite you again. So see you in a few months, hopefully. Keep up the great work, and yeah, thank you everybody for joining. See you guys all again same time next week. Have a good weekend, everybody. Thanks a lot.
okay.
Bye bye.
Goodbye.
Bye bye.